All right, so I want to show you a challenge that we have for talking about functions being continuous on an interval. So here is a closed bounded interval from A out to B. My interval I here is the interval from A to B. I've got my function g. And the notion of continuity that you've heard before, and this is actually a good way to think about it. I don't think I mentioned it in the first video, but that a function is continuous on an interval if when you sketch the function, you never have to pick up your pencil. There's no holes or jumps or anything like that. And if you scroll back up to the previous example that we did, you can see, oh, there's a hole, I've got to pick my pencil up. Oh, there's a jump, there's a hole, so on and so forth. So that's a good working definition. When we look at this particular function and we think about it, we say, okay, well, there's no holes, so this function seems to be continuous on this interval, and everything is fine anywhere inside the interval. All of these points are all good. There's a problem at the end point, though, and I want to show you what I mean. So to be continuous at, let's focus on A. To be continuous at A, the limit as x goes to A of g of x needs to equal g of A. Well, the problem is this limit doesn't exist. Why is that? Well, because you can only come from the right. You can't come from the left here. And so somehow that just seems like not a big deal, and it isn't a big deal. And so we're going to get around that. We're going to say, look, if you want to talk about continuity on an interval, then the limit of the left endpoint, you only have to come from the right, and the limit at the right endpoint, you only have to come from the left. Just avoiding that awkward situation where our definition sort of crumbles. And so let me erase this, and then we'll come back and talk about this in a minute. Okay, so here we go. Definition. So we're going to say f is continuous on an interval I. I might be an infinite ray starting out like that. It might be a closed bounded interval like we just saw. Lots of possibilities here. So we're going to say, let me scoot this down, that f is continuous on I if, first thing, f is continuous at all of the points inside I, so all the points that aren't endpoints. And I want to do a couple of things here, two things. So one, the limit as x goes to A from the right of f of x is f of A if A is a, let's think about it, we're coming from the right, so we want A to be a left endpoint of I, and then we want the limit as x goes to A from the left of f of x to be f of A as well if A is a right endpoint of I. And I say if because it may be that you have a ray that starts at a point and then goes out forever. There may be no right endpoint or no left endpoint, so on and so forth. And so now this example makes sense. You can say, okay, let's write down what we wrote last time. So even though the limit as x goes to A of g of x does not exist, but the limit as x goes to A from the right of g of x exists and is g of A, and so on and so forth. We'll say same for the limit as x goes to B of g of x. This one doesn't exist. You know what? Let's just do this. Let's erase same, and let's say this limit doesn't exist, but the limit as x goes, that's a sloppy arrow there. The limit as x goes to B from the left of g of x is, in fact, g of B. And so you can see that, so g is continuous on the interval I. The main thing that I want you to see here is just visually that we're going to go ahead and call, whoops, that's not good. We're going to call this situation, we're going to say that g is continuous on this interval. All right, well, let's end this video here, and in the next one we'll do Another example. Oh, actually, you know what? No, I've got one more example to do. I'm sorry. This example. So let's think about this function. F of x is square root of x, and my interval I is going to be an infinite ray, 0 to infinity. And I want you to realize that it's clear from the picture that the limit as x goes to 0 of f of x does not exist. Why? Because you can't come from the left. But even so, in this case, we still say that f is continuous on I. You should see that graphically instantly. And the key detail is that even though the limit as x goes to 0 of f doesn't exist, 0 from the right of f of x does exist. And that's all that we need. And that is f of 0, which is 0. Okay, now we'll break the video. In the next one, we'll look at some statements that we can use.